all we've established so far is the rotating magnetic field of the stator, right? There's still one more piece of the puzzle though. The rotor, right? We haven't made anything rotate yet except for the magnetic field. You guys look at this. This is your typical, we'd call a squirrel cage, right? What you have here is you have bars that, if you look, they're slightly skewed in here at an angle. These bars are all connected by this, it's called a shorting ring on each end. The reason they call it a squirrel cage is because if you took all these laminations out, you'd see these bars going across it. What can we call these bars? They become a conductor, right? What do we have here? A magnetic field, right? And if it's rotating, what do we have? We have movement, right? So these lines of flux are cutting, because they're rotating around it, going across it at every which way. We're cutting these conductors. What do we say were the three things we need for induction? A conductor, a magnetic field, and relative movement between the conductor and the magnetic field, right? Do we have those three things? So what happens here? We begin to induce a current onto these bars, right? That is why it's called an induction motor. Take a look at this thing. We have no electrical connection to this rotor. There's nothing. It's held in here by bearings. There's no electrical connection. It's all induction. What does that remind you of? A transformer, right? Your primary and your secondary have no electrical connection. There's just an induced voltage, right? That's what we got going on here. This guy sitting inside of here with that rotating magnetic field cutting across it, it's cutting across this at every which way, it begins to induce a current onto here. And what happens is it induces an opposing current. So we have a bar and a bar and a bar and a bar. What we induce here is it's opposing. So these are north poles and these are south poles. What happens in magnetics? Opposites attract. So what's going to happen when this magnetic field goes here? It's going to follow it, right? So now our rotor starts to follow it because of the polarity of these poles. And really what it's going to look like more accurately is we start inducing these currents on here, and these currents begin to flow on these bars halfway like this, right? They come down through here, conduct down to here, and then they start going this way in the bottom half, right? So what we end up having, this whole rotor actually begins to establish a north and south pole on it, right? Okay, what can we do with our left-hand rule? Current flowing this way, magnetic field around this conductor right here, it's going to go this way, right? Around this conductor is going to go this way, around this conductor is going to go this way. So we have this magnetic field being induced because the current that's induced on these bars, we create a magnetic field going this way. What about the left-hand rule here? Magnetic field is going the opposite way, right? What we end up doing is these combine and make what we call a resolute magnetic field. And it's going to the center of it, like that. And the opposite way, up here. Because all of these individual magnetic fields combine, and what we end up doing is we end up establishing a rotor that is going to look similar to this. Now, you place that in there, all you're doing is you're taking a magnetic field and you're putting a magnet, a north and a south pole magnet in there, basically. And so, as this magnetic field is going like this, it's going to follow it, right? No electrical connection, it's all on induction. And that rotor begins to spin around. Okay, now getting back to our speed, this thing is going 3,600 RPM. This rotor can't quite catch up. I mean, it's trying, right? And it's darn close. But it doesn't go the full speed of the rotating magnetic field. What that is called, it's called slip. Okay? So let's say, let me just say, what did we say earlier? 3,600 RPM? Is that what our motor was?
Yeah.
That's how fast the stator, that's the synchronous speed, right? That's how fast the stator field is. Let's say our motor has 2% slip, right? What's 360 times 0.02? Or not 360, 3,600.
72.
72. So you subtract 360 or 3,600 minus 72 RPMs. What do you get?
3528.
3528. So a motor that is rated that has 3,600 RPM with 2% slip, the rotor speed is actually 3528 RPM. It's being drugged along, right? That magnetic field's basically dragging it along. It's pulling it along, right? It's not locked in. And we'll learn about sync motors because sync motors actually lock in and stay right with it. Let's talk about this guy spinning around here. The faster it spins, the faster it gets to synchronous speed, guess what starts happening? The less lines of flux that are cutting in. Do you guys understand that? If it starts almost going the same speed as this magnetic field, these lines of flux aren't cutting it anymore because it's catching up to it, right? So what happens to our current here? It goes down, right? What happens to our magnetic fields here? They weaken, right? So the closer we get to synchronous speed, the less current we have on our rotor, the weaker the magnetic field, the weaker the torque. We don't have as much torque. Because really, when we're talking about moving something and talking about torque, we need strong magnets, right? We need a strong magnetic field. In order to have a strong magnetic field, we need to have high current. So the faster we get to synchronous speed, the closer we get to synchronous speed, the less torque we have. All right?
Startup amps kick up. Like
Okay. So the closer we get, we lose torque. Let's say we're almost up to synchronous speed. We're cutting less lines of flux. Our magnetic fields are weaker. Then we put a load on it. What does that do? It slows it down. Then what happens again? If it's slowing down, it starts cutting. These magnetic fields, they don't stop, right? The stator fields, they keep going. They don't stop. They don't care what's going on in the rotor. They just keep going. So if this slows down, and this is still going at the same speed, we start inducing more current back onto the rotor. What happens then? We strengthen these magnetic fields, and we catch back up. So that's why an induction motor can run. You put a load on it, and it's going to slow down for, you probably won't even see it slow down. It's going to react right away, right? Because as soon as you try to slow this rotor down, it starts inducing more current onto the rotor, which automatically, it's automatic. It starts to increase the torque, right? Our torque begins to increase here. So it automatically responds to the load.